My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar. So, good evening to all. I think you are well and safe from Corona pandemic. So, as we know that we are staying in a Corona pandemic situation, and situation becoming worse day by day. So, we cannot continue our normal academic program inside the campus. We have to start our online program. So, I think you have already come to know that the Department of Physics, Pabna University of Science and Technology, has started its online program, including online international physics webinar. And we have successfully completed our 233rd international physics webinar. Today, it's our 234th international physics webinar. And we have with us here today Dr. Dipankar Das Sarma sir, Honorary Professor, Solid State and Structural Chemistry Unit, Indian Institute of Science, Bangalore, India. And he has already connected with us. So I'd like to welcome our speaker. Sir, namaskar, and welcome to our international physics webinar. And thanks for accepting our invitation. So before going to you, I'd like to introduce you with our student and viewers. So dear viewers and student, I think you have already come to know the title of the today's International Physics webinar. That title is Small is Beautiful, Excitement of Nanoscience and Technology. And our speaker is Dr. Dipankar Das Sarma, Honorary Professor, Solid States and Structural Chemistry Unit, Indian Institute of Science, Bangalore, India. And he has completed his master's degree from Indian Institute of Technology, Kanpur, and his PhD degree from Indian Institute of Science, Bangalore in 1982. And then he joined as an assistant professor at the Solid State and Structural Chemistry Unit in Indian Institute of Science, Bangalore in 1989. And then he promoted as a assistant professor in 1993 and as a professor in 1999. And from 2021 to present, he is working as a honorary professor at the same institute. So thanks all of your patience, and it's time to go to our speaker. Sir, it's your time. You can start your session. And thanks again for giving us this opportunity, sir.
Thank you very much, Professor Das. I hope you can hear me so that others can also do. I'm going to share my screen and then let me pick up the laser pointer so that you can see. Okay. So as already announced, my today's talk is going to be Small is Beautiful and Excitement of Nanoscience. This small is beautiful is really, as you can see here, is to take a big object and then we start to break it down into smaller and smaller object, and it becomes so small, like here you cannot even see it's written small here, and that is the limit we are going to explore. In fact, we are going to explore a limit that's much smaller than what I'm showing you schematically here. And why? And that going to that very small limit defines what nanoscience and nanotechnology is. And I'll try to tell you about a few aspects of why it's a very exciting science and technology field, which has opened up to us over the last 30 odd years and given rise to many interesting phenomena. Let me start by defining what I mean by nanoscience and nanotechnology so that we know exactly what we're going to talk about. It's really the limit where size matters. What do you mean by that? Normally, imagine that you are considering you have a block of gold. If you're very rich, you have a big block of gold and you divide it into two parts. Then you'll have two parts of gold, half the volume each, but its intrinsic property will remain exactly the same. It will look the same, its metallic nature will remain the same. Every property that is intrinsic to gold will remain the same in both the parts. Think of taking one of these parts and dividing it again into two halves. It will again remain exactly like gold. But if you go on dividing like this, such that you reach a limit, a very small size limit, and I'll tell you what the size you need to get to in a moment, you'll find that the property of gold begins to change. It is still made of the same gold atoms, but when there are very few of them left, gold is no more having the golden color. In fact, it ceases to be metallic when you go to very small size. It can be even made reactive. So that's why I'm saying size does matter. But size matters in the direction of becoming small. Actually, it's most of you didn't see the movie Godzilla when it came originally. There used to be an advertisement which actually used this saying size does matter, but the size mattered because the Godzilla was very big. But now we are thinking of Godzilla being very small and becoming smaller and smaller, and I'll show you why in this small limit the size matters. Sometimes I like to change the title and I say it is the story of the least, the smallest size particle. At last, we have come to that story. Now, let me start by defining exactly quantitatively because physics is all about quantifying. What do I mean by nano? The word nano is actually a Greek word and it means dwarf, small, very small, and that the scientists use to define nano as 10 to the power minus 9 because it's a very small number. And if you put a unit after that, for example, 1 nanometer, then it becomes 10 to the power minus 9 meter, which is equal to 10 angstrom, as you know. You could have talked about 1 nanosecond, 1 nanogram, 1 nanokilogram, whatever. It would imply 10 to the power minus 9 of that unit. Now, this nanoscience is really the regime where the material dimension, one of the dimensions, for example, a three-dimensional object have the length, the breadth, and the height. One of the dimension gets down to in the nanometer range, 1 to 10 nanometers, at the most 1 to 100 nanometers, not much more than that. Depending on the material, you have to go to that size, and you'll find that the properties begin to change, the intrinsic properties begin to change. That's why you call it the nanoscience and nanotechnology, implying in the nanometric regime, when the properties change, then using those changed properties. And I'll show you, taking diverse examples, how fantastic things and fascinating things can be done. But it's a very, very broad area. Let me tell you, because of we don't know if I say 10 to the power minus 9 meter or 10 angstrom. What does that mean? Think of human hair. Human hair, thin hair like mine, very thin, is still 100,000 nanometer wide. So to get to 1 nanometer, you have to take one hair and split it 1 lakh times vertically to get to 1 nanometer size. That's the small size that you are talking about. It's exceedingly small. Before I start telling you about nanoscience and nanotechnology, this is a story all of you know possibly. This talks about six blind men, wise men. They heard about elephant, a new animal, and they wanted to figure out what this animal is like. They're like scientists. So what do scientists do? They do experiments. So these scientists got hold of an elephant and started doing experiment. One scientist was touching the tail and said, aha, I know. Elephant is like a rope because he felt it's like a rope. This scientist was touching the body and found it big and wide and flat. Said, no, no, elephant is like a wall. This fellow was touching the feet and thought elephant is like a pillar. This fellow was touching the ear and thought elephant is like a fan. This fellow touching the tusk of the elephant thought it's like a javelin. And this fellow touching the trunk of the elephant thought it's like a snake, big fat snake. So each of them had a different perception what elephant is. Nanoscience, nanotechnology is exactly like that. It's a very vast subject that covers physics, chemistry, biology, medicine, every form of engineering. So everybody has a different perspective of what nanoscience and nanotechnology is. And it would be impossible for me to give you a flavor for all the sides, so, or go too deeply into one aspect. So what I decided to do is to take a few examples covering different areas of nanoscience and nanotechnology so that you get a flavor for the wide variety of things that can be done. Of course, the ideal way of knowing what elephant is would have been if all these scientists sat together and described to the others what elephant is like. This guy is saying rope, that guy is saying wall, this pillar, this guy is saying fan, javelin, and snake. And then they could have put together all the description, and then they would have come to know what elephant is like, which would be like this. Of course, this looks like an elephant, but its property is not like an elephant. So even these part descriptions, when you put together, we don't get full appreciation for what the subject is like, but we'll try our best to get an appreciation for this field. So this is the amazing world of nanoscience and nanotechnology that I'm going to talk about. There are actually 4 different aspects where I can broadly categorize that one can have advantages in going to nanometric size. One that I'll talk about right in the beginning is that as you make the size of the material small, the surface area increases. And that's a very straightforward concept. It's been there in catalysis for a long time because all chemical reaction takes place at the surface. So if you increase the surface area, then the total reactivity would go up. But nanoscience, nanotechnology talks about not only increasing the surface area, but the catalytic property itself changes because you go to such a small size. I may not talk about that, but I'll give you an idea about how surface area increases very quickly. And then when you go to very small particle size, many of the physical properties begin to change, and this is what I talked about. The material strength can change, it can become harder or softer. You can make use of different particle sizes to achieve much higher packing density. It has very important consequences in metallurgy in terms of sintering, etc., all of which I'll not be able to go into, but I'll give you 1 or 2 examples of. And then it gives rise to tremendous flexibility of functionalizing. And I'll give several examples from this particular category. So I'm not trying to explain what I mean by that right now. That will become evident as I go along. And there are examples of in biological, electronic, optical, and sensor applications. And then a very interesting thing has happened. I said that gold, when made very small, doesn't remain metallic anymore. Its color, it changes from golden color. That means both its electrical and optical properties begin to change. And you can tune the electronic property and optical properties by taking it to very small size, and I'll give you some examples of that also. These are let me get started with the first 2, and I'll give quick examples of them, and then I'll spend more time in the next 2 categories of examples. Now, about the surface. Now think of, you have a cube. If I make a square of side A, you know that the area is A squared. If I make a cube of all sides A, then the volume is A cube. I've kept it here, it's an A cube volume. It has a 6A squared surface area. Take the same cube, break it into 2 parts as I have done here. So the total volume remains the same, A cube. But now you see I have introduced an additional 2 surfaces of A squared. So from 6A squared surface area, now the surface area will become 8A squared. So I put it there. Now think that I am breaking it into 16 cubes, 4 this way, 4 that way, 4 that way. The surface area will become 24A squared. Always volume remaining the same. This will become 48A squared. Now you can see that as I'm taking the same particle, breaking into smaller and smaller pieces, very quickly the surface area is increasing and increasing very rapidly. And that's how the surface area increases, and it gives rise to total reactivity more, which is in catalysis that I talked about. But actually, when you go to very small size, the catalytic property itself changes. And that is when we talk about nanoscience and nanotechnology being used. So I'm talking about the surface. Now, I said that reactivity is on the surface. Let me try to quantify for you to give you some quantitative idea of how many atoms and molecules are on the surface. Let me take one particle, and I'm going to take a very small particle, a grain of sand. In fact, I'm going to take a grain of sand that's very, very, very small. You can hardly see one grain, such a small sand I'll take, which, let's say, each side dimension, it has a diameter of 0.01 millimeter, so about 10 micron. In such a fine sand, 10 micron, 0.01 millimeter diameter. There are altogether about 10 to the power 9 molecules of sand, silica. And 1 in every 10,000 molecule is at the surface. So the percentage of molecules that are on the surface, as you can see, is 0.001%. Now think that I make this sand much smaller. Here is a dot I have put, and I have reduced its size by 10,000 times, so that now it is in the order of 5 nanometer size. That one has a total of 6,350 molecules. And in that, 2% of the molecules are on the surface. So you can see that if here you had only 0.001% was on the surface, here you have 2% on the surface. So the surface properties become very, very important. So there are so much of surface when you get to the nanometer regime that you have to really think of the surface very carefully. In fact, one of the obvious advantage would be, think that you are painting a wall. Typical paint is some colloidal particle of dye, and think that they're very small, this 10 micron, as I talked about, this very fine sand. A 10 micron particle will cover, this is the wall that I want to paint, a 10 micron particle would cover only 10 micron area. But if I break down this 10 micron particle into 25 nanometer size particle, then I can spread this particle over a very wide range, and the coverage will become 1 million times more compared to here. So that what was covering only 10 micron area will now cover 1 million times larger area using the same amount of material. And that is the kind of advantage you can get. But how do I make this nanocrystal? One of the ways is that you take a big crystal and you break it down. You break it with a hammer, you can cut it, you can chisel it out, and you keep doing that till it becomes very small. It's called a top-down approach. Top-down because you start from big, from the top, and break it down into smaller one. And that's, as you go down, it's becoming smaller, and that's why n is very small, you can hardly see it. Once you reach the nanometer regime, you'll not be able to see it. This is a physical method. There's a chemical method where it's exactly the opposite way. Think that I'm making zinc sulfide. Think that this is a zinc atom, and its zinc atom has 4 arms. It likes to hold sulfide ions with each of those hands. If I put a solution where zinc ion is there and sulfide ions are there, this zinc ion with 4 arms will catch 4 sulfide ions. So I'll get this ZnS4 unit, which I call the one layer. One layer of sulfide has come. There are 5 atoms in this system. But these sulfides are also each of them 4-armed. So they are not happy holding one zinc. With their other arms, they want to pick up other zinc. Those zinc in turn want to pick up other sulfur. So when 3 layers are formed, you get this object, and the number of atoms become 41. This process can continue, and then you're growing the nanoparticle from inside, and it's growing bigger and bigger, and you stop the reaction at some point to get a nanoparticle which can be 5 layers or 6 layers, 7 layers, 8 layers. You stop the reaction and you get these nanoparticles roughly spherical in size or faceted. This is called a bottom-up approach. That means I'm starting from the smallest unit and becoming larger. That is what I'm doing. Can I actually do such things? Seeing is believing, so I'm going to show you. As I said, such small particles you cannot see. So we use transmission electron microscope to see them. Excuse me, because I've got a very bad throat since yesterday. So I'll be clearing my throat once in a while. Bear with me. So transmission electron microscope. So here is a transmission electron microscope, and each of these small dots you are seeing is actually cadmium selenide nanoparticles. There are so many nanoparticles. If you want to see them better, I can focus on one of them, and it looks like this. What you are seeing here is the atomic planes of cadmium selenide nanoparticles. We can go even closer to it. You can see the atom columns. of cadmium selenide nanoparticle. This is one cadmium selenide nanoparticle. Other nanoparticles are on the sides. So you can really control the size down to nanometer size and make these nanoparticles. They are not only spherical, they come in all kind of shapes. Here is an oval potato-like shape. You can see rod-like shapes. These are stick-like shapes. There can be bends, and there can be, it's like the comb. You can comb your hair with it. So every kind of shapes and sizes of nanoparticles could be formed. And at one period, about 20, 30 years ago, it was very popular to make different shapes and sizes, because depending on shape and size, the properties change. But why should we be interested in it? Now, if you think of your computer or your mobile, the mobile that you're using to listen to my lecture, you can do that because that's a smartphone. And that has chips that are more powerful than the huge computers that we used when I was a student of your age. The 1971, it was each transistor that are used to make the chip, computer chip, which is on your mobile, were 10 micron in size. So one chip that one made in those days had about 2,300 transistors in it. That processor name was 4004. Very rapidly, the transistor size were made smaller and smaller and smaller. You can see how the transistor size went down, become 1 micron. In 1989, that's when Intel 486 came in. Then it became 800 nanometer, 350 nanometer, 250 nanometer. Each transistor of 180 nanometers. So in the same size CPU, originally I had 2000 transistor. Now in 2000 already we were putting 42 million transistors there. And that is why we can give you on your mobile the computer power that is much, much higher than the computer power that the computer had in my college, which was one of the best colleges. And that computer occupied 2 huge rooms. And on the palm of your hand, you have a computer that's much more powerful than that. In fact, we have not stopped there. Continuous improvement has taken us now. In fact, in 2019, the size of transistors have become less than 10 nanometers. And that's the kind of size we are talking about. That's the kind of huge number of transistors we are packing in a CPU. And that's why we're being able to process faster, store faster. Everything has become much smaller. And that's why people are so excited about making things small. And many of you may know about Moore's law. Mr. Moore had said that the computer chip power doubles every 18 months. There are equivalent Moore's laws, equivalent laws in every other. For example, size of the storage device. Even I talked about sensors and actuators. Our life is going to be completely controlled by sensors and actuators. Today, modern vehicle, modern cars already have 60 to 100 sensors. Very soon, the smarter cars would have more than 200 sensors. Every part, every aspect of car would be monitored by sensors. And 200 sensors per car would mean that we would need 22 billion sensors to populate all the cars that are there. So you can imagine what is the number of objects that are going to be required very soon. So we need very small devices, pervading space everywhere of our life. So continuing with why do we need to make things smaller? I was talking about storage device. You know, your mobile, my mobile, has this megabytes of memory, megabytes of terabytes of storage space. How is that possible? Think that one bit is this size. If I want 100 bits, I'll need this much space, right? So my mobile, if it needed 1,000 bits, then it won't even fit here because it's not 1,000. So only way I can get 1,000 bits of information in this small mobile is by making each bit size that I have shown over here. Each bit size has to become much smaller than what it is here. For example, let's take the hard disk. Some days back, these are slightly old numbers, but it serves my purpose of illustrating. Every gigabit of storage space that you wanted would weigh 100 gram. So if I want 10 terabits, in fact, now my mobile, this one I think has something like that. I don't even know how much it has. I think it may have 1 terabit of memory. That is 10,000 times more. So 10,000 times of 100 gram would be 1,000 kilogram. That's 1 ton. I wanted 10 terabits of memory storage space, but I don't want ton to be on my laptop because then my lap will collapse. So in order to have this huge amount of storage space, I must make each element, each bit much, much smaller. So in order to do that, we really need to be able to manipulate, to make things at atomic and molecular level and manipulate them, put this make them at will and put them at will where we want and get the property at will what we want. In order to do that, in fact, this is a very famous statement from, let me check because I'm afraid that, yeah, okay, time is okay. In the early 1950s, Richard Feynman had made a very famous speech which made this sentence very famous. There's plenty of room at the bottom. And he had made some challenges. There's like also Alice in the Wonderland. Those of you who have read the story, Alice drinks a potion and keeps becoming smaller and smaller. And she says, what a curious feeling, I must be shutting up like a telescope. So this is what we are going to do. But let us get some ideas about how small things can be. There's this very famous poem by William Blake that I like, which says that to see a world in a grain of sand and heaven in a wild flower, hold infinity in the palm of your hand and eternity in an hour. I'm going to use this particular poem in a particular way. I'll talk about the grain of sand and I'll take the palm of your hand and then ask the following question. I'm going to collect sand, very fine sand, as I told you, 10 micron in diameter. I'll take a heap of that sand on my hand. If I want to hold it in my hand, let's say it's 4 centimeter by 4 centimeter by 4 centimeter heap. And each sand, this very fine 10 micron size, I'll use it as one bit. So I'll store one bit of information on that. And I'll ask how much information can I hold on the palm of my hand? That means I need to calculate how many sand grains, this fine grain will be there in this volume 6 into 10 to the power minus 5 cubic meter, which is equivalent to 4 centimeter by 4 centimeter by 4 centimeter heap of sand. With a density of sand of 2.65, its weight is about 170 grams, which is not too bad. And since I said it's going to be very fine sand, 0.01 millimeter in diameter, I can very easily calculate, and you can also calculate. You'll very quickly find that if you calculate through, that there are 64,000 million grains of sand in my hand. That means 64 billion. 1,000 million makes billion, so 64 billion grains. That means if I write on each of those grains, I can write 64 gigabits of memory. 64 billion is 64 gigabits of memory I can have, which is a very large number, which is nice. But imagine that I want even more. And somehow I'm able to write on every molecule of silica, SiO2. And I take just that one single grain shown over here. But instead of writing one bit of information on one grain, I'm going to write one information on each of the silicon dioxide molecule that is there. So let me ask how many SiO2 molecules are there in such a fine sand. If you calculate through quickly, I'm not going to go through it. You can do this calculation easily. And you'll find that this heap of sand that I talked about, if you wrote information on each of the sand grain, you can write 64 gigabits. But instead of if you take one grain out of that and write on each of the molecules, you'll be able to write 26.6 terabits of memory. Because there are 2.6 into 10 to the power 13 molecules there. So the question is, can I actually write? Can I actually manipulate at the molecule atom level? And this is what I'm going to show you next. Do I have that ability to manipulate atoms and molecules, put them where I want, store information in them, and extract information in them? Before I do that, I'll tell you how we study different length scale, different sized material. You know that as I'm looking to smaller and smaller size, I need to use microscope. Optical microscopy can show you in this range and not much smaller than that. Human hair is here. As you make things smaller, integrated circuits coming down, now reaching down to here, you can use electron microscopy down to that size, biological macromolecules, and atoms and molecules are in the 1 nanometer size. So now we have transmission electron microscope, which is resolution better than that. And we can also use scanning probe microscopy, both to see and manipulate, to put them at the right place. Let me quickly give you an idea about scanning tunneling probe microscopy by an analogy. If I put marbles, many of them together, and if I took my finger and moved my finger across that marble stack, I would feel the marbles go up, come down, go up, come down. So I'll be able to count the number of marbles. If I want, I can use my finger to move a marble from one place and put it at another place like this. Of course, I cannot do it atoms and molecules because my finger is too gross. It turns out that I can use a so-called finger, which is a collection of atoms like this, a tip at the front of a metal, which can act like a finger exactly like this. It senses, here I sense by nervous response. Here, the way I sense is I apply a voltage between this tip and the material that I want to study. And then current begins to flow through the small gap of a few nanometers by tunneling. And you can see that the tunneling current will increase every time the atom comes closer, so the gap becomes smaller, and the current will go down when the atom goes farther. So by monitoring the tunneling current, I can feel whether the atom is up or down. And using the same thing, I can also drag it and put it at different places. This is the technique that is actually used here. What you are seeing here, each of these things is actually an iron atom put on a flat plate of copper. Here is a full image. Each of these is an iron atom that has been placed, dragged from elsewhere using the STM tip, arranged in a round circle, and then this copper, what you're seeing, the copper wave function of the copper electron density inside, and this is a standing wave it has created because you've created this quantum coral all around. And outside, so this is a confined space, and so the electronic property change inside, and you're seeing an image of that. Outside, these are the electron states outside, and they're not confined, and so they look different from what they look inside. But the important thing to see is that how beautifully you can arrange the atoms all across. Here are other examples. Here again, iron and copper, and its Chinese character, kanji character, which reads atom again. It is in kanji character. Here, carbon monoxide has been arranged on platinum, looking like a man. And here is xenon atom on nickel. And you can see what is written here, IBM, because this was made in IBM research laboratory. And then also imaged using the STM. So we are really able to manipulate and read at that level. We can also make transistors down to using a single electron, and this is one example of that. What I'm showing you over here is silicon, which has been doped with one tellurium here. And tellurium's outermost electron is very loosely bound. And there's a barrier layer of silicon dioxide here. And then I have the source and the drain aluminum leads, and this is the gate. This gate electrode is also aluminum, and I'm going to apply potential here. When I apply an attractive potential here, this electron gets attracted here. And when it comes closer together, it's like this electron has these levels, and these levels you'll see will move up as I apply a potential. The gate potential is being applied here. Simultaneously, you'll see this dot will keep moving. As soon as this level comes in resonance with this outer pharmacy of these aluminum levels, that means this localized level comes here at the correct gate potential, electron will be able to tunnel through from this end to that end, from the source to the drain, and suddenly the electron current will increase. And then if I increase the gate potential more, it will move out. So again, it's not in resonance, it will not flow through. And that is the way this gate potential will control the current flowing through. And so that is essentially making a transistor using a single electron. And let me show it to you. I have to possibly get rid of this one. And no, not pen also. So get rid of the pen. Okay, now. Okay, you can see how every time this level comes there, it goes up. Reverse again, goes up the current. So the current flow through the source and the drain can be controlled by the gate voltage, and that is the principle of a transistor, using just one electron's property. You can do a single atom transistor. People have done it. I'll not explain these things. You can do a single molecule transistor, but I'll show you a few other examples. This is not a transistor at all. This is a nanocar, where synthetic chemists have put together this molecule, which looks like a car with these are the wheels. And you can see that this object here can rotate around this bond if it put in the right way. So those are the four wheels, and there's a body, rigid body. And depending on how I put, these wheels can rotate this way or it can rotate that way. If I put all four wheels in the same direction, in the same way, then the car can move forward. But imagine if I put this one in one direction and this is another direction, then they will oppose each other, they cannot move. And I'll show you such construction. So basically, the idea is these molecules will move and the entire object will move forward. Okay? So in this case, here is the molecule. You can see the molecule will start from here and will end up here. It is the starting position, and you'll see by steps it will go up to there because I've put these wheels in the right direction. Let me show you that. The molecule starting from here and rotating and moving up, and it will end up there. Okay? Now in the next example, I've put the wheels in the opposite direction. You can see, so that it won't move. And this is the trajectory. It will not move. Its starting position and ending position are the same, and I'll show you that. It's trying to move, but it's not being able to move away because the wheels are in the wrong alignment. Now imagine this situation where I've put these two in this direction, these two in this direction. What it will do? It will start to rotate and have more random motion rather than this linear motion. And here is the object shown that way, and that is what you'll see happens here. It will rotate more than it will translate because I've put the wheels in such a way. Now I come to the later part of the discussion, and let me show you how I can change the optical property. What I'm showing you here is one single material, cadmium selenide. But the particle size of cadmium selenide is different in different vials. The color change that you're seeing is scattering. Don't worry about that. We are interested in the luminescence color, which means I'll shine UV light on it. It will excite an electron and hole in the system. That will de-excite to give out light, which is characteristic of the material. This is the way the light bulbs work, the tube lights work. They have all fluorescent material. Your screen works, they have some kind of fluorescent material. It could be electrofluorescent or photofluorescent or luminescent. So these are luminescent material. Cadmium selenide, here the particle sizes are larger, here the particle sizes are small, but all of them the same chemical And if I shine light on this, it gives me this blue light. This one gives me this green, this one gives me this green, this one gives me yellow, this one gives me red. So out of a single material, cadmium selenide, just by changing the size, I can change the color that comes out of it. And then you can imagine what power it would have. All your display materials can be made from one single material just by changing, controlling the size. Why does the color change? Because the electronic structure changes. And why does the electronic structure change? Let me tell you very quickly. This is the musical instrument that you might have played, an accordion. It's depending on length, or a flute you can think of, the frequency that comes out. So electron in a box, all of you are physics student, you know electron in a box has the energy levels, which goes as n squared over a squared, where a is the box length size. 2a is the box length size. And these are the discrete levels of the electrons. Imagine that electron is filled up to here and empty there. Then the band gap that controls the photoluminescent behavior is the energy difference between these two levels. So let's focus on these two levels only. Okay? And let's think this has the principal quantum number n is equal to m, then this is n is plus 1. So m squared over a squared, and it is m plus 1 squared over a squared. So the energy difference between these two is delta E, which you can see the difference between these two, it goes as 1 over a squared. So if I make the box size smaller, the energy difference will increase. So as box size decreases, the energy separation increases. And this is exactly what we do. Because in photoluminescence, what happens, a photon comes in, excites an electron from the occupied state to the unoccupied state. Then it recombines, and the energy, excess energy, comes out as a luminescent photon. And that's the color we see. So when the color is changing by changing the size, that means this band gap is changing. Can I monitor that? Let me show you that we can monitor. Because what I'm saying, that particle size, when it changes, either the conduction band goes up or the valence band comes down, so that the band gap changes, and so the color changes. So I need to be able to measure the band gap. How can I measure the band gap? It's very easy. Come in with photon. If the photon energy is smaller than the gap, this much, let's say, then an electron cannot be excited, because energy conservation requires that you give enough energy to take one electron from here to there. Now you increase the photon energy a little, even this photon will go through, it will be transparent, it won't absorb. The moment the photon energy becomes equal, these electrons will begin to get absorb photons, so you'll see a part of the photons are getting absorbed. So if you're monitoring, if you are passing photons through a material and monitoring it on the other side, the detector, suddenly the detector sees the photons that are being sent and not coming through. That means absorption is taking place, and that is equal to the band gap. That is exactly what is done. You can see here it is not absorbing. There's the photon energy. There's the absorption. Suddenly the absorption begins to increase. That means it has a band gap here. These are all cadmium sulfide different sizes. And you can see how the band gap changes. You can see the absorption edge starts at different places, how it changes. So I'm being able to, here is another example of zinc oxide, whose band gap can be changed over such a wide range of energy just by changing the size. And that's how we change the color. And once we change the color, we know that colors combine. And when colors combine, I can make white light. I can use it for lighting up my room. This is how your LED light can be made. And here is an LED light that we actually made by combining the colors, and you can see the white light coming out here, etc. Other applications, I'll give some biological applications before I end, because that is also an important area. For example, it can be used for detection. These very highly fluorescent materials, you can connect it with biological materials, and with the property that those biological materials have the propensity of going and attaching itself to cancerous cells. So that it can go, you launch it in the system and it goes and attaches itself to the cancerous cell, and then you excite it from outside with photon, and they glow, and you know exactly where the cancer cells are. So they can be used for such purposes and many other purposes. This is just one example. You can not only do that, you can also attach molecules or drugs with it. Normal drugs, what they do is like carpet bombing. These are, imagine, cancer cells, and these are healthy cells. You want to only kill those. In carpet bombing, both these cells and the healthy cells die, and so it, as you know, that it is a very hard treatment, chemotherapy. But you can make nano devices, nanomedicine, which are targeted, which will go and attach itself exactly to the cancer cells. Once it attaches them, you can from outside trigger them either by magnetic pulse, electric pulse, or photon pulses, such that they get excited and release a medicine, and exactly the cancer cells are killed, and the healthy cells don't get any dose of the medicine. And so the dose needed is much smaller. And this kind of actual drugs are being created today. I'm giving you an example of that. In order for this drug to go into the bloodstream, you must give solubilizing group, meaning you make it hydrophilic, and this is the hydrophilic groups are attached, and you make this structure, dendritic structure. Then you can attach small drugs in that. You can make large encapsulated drug, and this entire unit can be launched into the bloodstream. And you can also give targeting moieties. These are the targeting moieties which find where the cancer cells are. So they go and attach themselves to the cancer cell and deliver. These allow you to get into the bloodstream. These allow you to find the cancer cells, and these are the drugs that they delivered on the cancer cells. And that's how the cancer is cured today. With this, let me end my talk, thanking you for your attention. Thank you very much.
Thank
And
you, sir, for your wonderful and exciting presentation, sir. So we have got few questions. So if we allow, we can start our discussion
sure,
session.
yes. You can change back the screen because otherwise
Yeah,
there's infinite regression.
no, I can.
Okay, I have to stop screen share. Yeah.
Yeah, okay, I
Okay.
can add the question in the screen so that you can also see.
Okay.
The first question: is there a measurement smaller than hectometer?
Well, you've got me there. I don't even know how much yoctometer is. So, will somebody define the yocto for me?
Okay, maybe we can get answer from the audience
Okay.
later. I can go to the next question. So the next question: why do we use electrons to image nanomaterials?
It's a very good question. See, the point is, it's actually there's very nice, easy answer that you can understand. I can see with my eyes things that are illuminated with visible light, right? And visible lights have a wavelength in the range of thousands of nanometer, in the order of 1000 nanometer, let us say. 500 nanometer, 600 nanometer. It's in that order, green, yellow, orange. So let's say 500 nanometer objects. When objects become much smaller, now the object has a size that is smaller than one wavelength of the visible light. So there is the visible light does not interact with it. It's too small for the light to interact. So I need wavelength that would be the size of the material for the wave to interact with the material. So I need to, since I'm talking about nanomaterial, the wavelength that I need is in the range of nanometers. Electron wave is in the nanomaterial or angstrom range. And that's why you use electron wave property to image nanomaterials. Okay?
Okay, sir. Thank you. We have another question. So is there okay the same question, and there is another question. So is there anything smaller than jet
I
substance?
really don't know whoever it is. Let me admit my ignorance. It's one thing very important to tell what you don't know so that you can find out the
Oh yeah,
answer later.
yes. So there is another question: so how nanotechnology could
Okay,
help
it's again
to particle?
outside of my domain, but you can immediately see that detectors can be made much more efficient, and that's happening all the time. Detector development. First of all, the particle physics, all experiments involve tremendously complex experiments that require heavy power, high detection, high computation, high bandwidth of transmission, and all these aspects get extremely influenced by improvement in the electronic devices. And that is happening all the time because of advances in nanotechnology in electronics and in the detector technology. Okay, so that's being influenced very, very heavily. In fact, particle physics, experimental particle physics drives in many ways technology in this sector because they are so demanding in their applications. And then the technologists come up with solutions using nanotechnology to meet those demands.
So thank you. And this may be the last question. So, how do scientists discover and measure massless unit of time? So, smallest unit of times, and like femtosecond and zeptosecond. And what do they use, and what is the needed, and how are the cameras created?
There are many questions involved here. Not all I can answer. Many things are done by interference methods. The so basically you use different wavelengths or time delays because you see the point is that if you want to measure difference in events and you have the possibility, imagine that you have the possibility of measuring very fast events and light travels very fast. So if you move the light by traveling path by a small amount, the time difference between those two paths is can be made very small, and this path difference can show up as an interference pattern which then can be detected. So that would be one of the ways, right? There are many different ways that it can be done. So I'm just trying to give you one example. Others, I'm not even an expert to give you an answer of, but you can find in the internet easily some of these answers.
Okay, sir. So before going to end, I got another question. So why can't we see
It's
God?
the same person who's
Yeah.
extremely curious. You cannot see, as I said, that we cannot. Seeing is using your
Another
eye.
question similar,
Oh, I think
like,
it's now becoming a bit
yeah.
ridiculous. I don't think the
Okay.
person is even interested in knowing the answers, is more interested in asking the questions. So I don't think I should indulge in that.
Okay, sir. Thank you. Thanks for your wonderful presentation. It is a great opportunity for our student to interact with you in this nanotechnology. And thanks again for giving us this opportunity, sir. So bye for
Thank you.
today, and hopefully in near future we can arrange another webinar with you, sir. Have a nice day,
Thank
sir.
you.
Good night.
Take care, all of you, and stay safe.
Bye, sir.
Bye bye. I take leave.